Thank you to everyone for being here and welcome. This is Ander, and as you already know, today my plan is to talk briefly about different strategies for large-scale printing of thermoplastic composites. What I'm going to do is to focus all the information, all the techniques for cryogenic storage. Why? Because this is a very technical application, and that requires a very, very huge preparation, a control of the process, and of course, high and good results. First of all, I'm coming from IMEN. It's a research center that is located in Galicia, in the north of Spain. And mostly what we are doing is research, development, and innovation activities. And we cover the full range of applications from materials, advanced manufacturing, digitalization, and sustainability. As you can see, when we talk about additive manufacturing, we cover 4 different technologies. The first one, like automatic fiber placement, the fused filament pellets fabrication, direct energy deposition, and concrete printing. But my topic is the thermoplastic materials, and this is like FFF, or commonly named AMF. Well, we work in different areas, and mostly in mobility and aerospace. As you can see, we cover around 20% of our projects focused in aerospace. And this talk is framed in the OVERLEAF project. This project is focused in the storage of liquid hydrogen. That means that we have to decrease the temperature of our materials and of our prints down to 20 kelvins. And this process would do is to generate huge stresses into the material because the thermal compression. Well, this is the consortium, and we are working both in Spain and in Europe with different partners from everywhere. This is the main idea of the project. We want to generate an inner tank, then place foams around it to avoid the cold temperature to go outside, and then an outside tank to stop the leakage of any hydrogen. And this is what I'm bringing today. Probably all of you know how to print it. This is a small print made with the same material we are using for the inner tank. This is, as you can see here, 0.5 millimeter thick, 0.25 millimeters high walls, and it's printed around 300 degrees and 50 millimeters per second printing speed. Well, this is very easy to print. Probably all you know. This was made in around 10 hours of print. We spent around 2-3 hours planning the print, like changing different materials. And well, it was printed really, really well. This is the tank. This is the real model that we're going to print. This is 1.5 meters tall. And this, compared with a human of average size here in Germany, as you can see, means that it's huge. This completely changed the way we are working, and of course, like the different steps that we have to spend to achieve our goal. This requires around a year of work of a whole team developing the model, planning the different prints, developing the material that we require. I mean, planning everything. Every small step must to be planned because this, again, is very technical and it must to be everything perfect. And this was yesterday. This is my colleague that is right now printing the real scale tank in PLA, of course. This is why we are watching like white color below, black upstairs, because what we are doing right now is one of the end steps, that is to check if everything is running perfectly, smoothly. This was around 24 hours print in total. And today, I don't know, it will be around 100 hours. Well, this is a brief list of small steps that I developed that you have to consider when moving from that small scale to the large scale. Let's try to cover them. Of course, this will be very brief, and I will talk as more details of each step, but please, if you are interested in anything, come to visit our stand, come to talk with me, because I will be more than welcome to talk with you and discuss everything you want. Well, what is the first step? Material selection. We want to decrease the temperature down to 20 Ks. So that means that we have to select very well the material. If you make a wrong selection of material, everything will be bad. So the first step, you have to decide which are the requirements of your application, what's going to happen, how it will behave, and then choose the material. In our case, this is a polyamide with basalt fibers. This was selected after several tests, thousands of samples, a lot of different mechanical, contraction tests, TTS, and finally, we choose the right material, or one of the best materials possible. In this case, these materials have an extra option. This is fully sustainable. We are talking about sustainable fibers, bio-based matrix, so not only have a good performance, but also is sustainable. Well, what we have to consider as our critical point, the temperature. So we have to test very well the temperature of our material, and if when it's printed, it is able to stand the 20 Ks that the application will require. Well, we developed a whole system to test those temperatures, the mechanical properties at those temperatures, and it was successful. So next step, warping. Thermal stresses. Probably all you know what's happening when you are printing a material. We have warping, and sometimes the material and the bottom of our pieces is not perfect. That is not happening in larger scale. In larger scale, you have a completely destroyed shape. I mean, the warping generates huge tensions, and when the tension doesn't generate warping, what generates is cracking. This is happening because the adhesion between layers is not good enough. So you have to ensure like the layer adhesion, like the tensions are decreased, and the layer adhesion is improved to ensure that your material will stand all the mechanical requirements that your application will have. Well, what is the second step? How to deal with the different printing conditions to decrease as much as possible those thermal defects while keeping the same material, while keeping like the similar conditions. For example, in this case, this is not the same material, but it's a good example. What we did was test a full range of different applications of different conditions, only to show you how a small change in the printing conditions at large scale can modify the print. This actually is not the actual size, but the models were around this, and you can see that we are having like a huge warping. So this was very visual, and as you can see, only by decreasing the layer height from 2 millimeters to 0.3 millimeters, we decrease the warping more than 5 times. So second, we have to be very careful with the printing conditions. And finally, the reinforcements. I already talked about basalt fibers, but this is a huge wall of different fillers that you can choose to improve your material properties. We have particles, we have short fibers, and we have continuous fibers. Each one behaves completely different. Each one defines your printing conditions. And that, because that, you have to be very careful what you choose and how you apply to your print. In our case, we choose the short fibers. Why? Because they allow us to reinforce our material while keeping a good processability. Why? Because the tank is super complex. This is mostly a ball. But inside our tank, there are several components that must be assembled, must be printed, and that is why we need a good accuracy, a good mechanical stability, But at the same time, we need, like, it must be thin to decrease the weight of the tank. It must to be mechanically stable. So there are all the requirements in one. So finally, short fiber were our choice, and well, they are performing quite good. Next, layer adhesion. When we are printing in low scale, layer adhesion is not an issue. This is true. I mean, when I was coming, I broke the tank because, you know, it was in my backpack. But we are developing a demo, and the demo is OK with a quite good layer adhesion. So actually, this is strong. But that is not happening when you are printing large scale. You have to ensure that the layer adhesion is perfect. And that is why, usually, what you require is to heat up the substrate. That means you are not only heating the printed bed. You have to heat it up each layer just before you are printing the consecutive one. Why? To improve as much as possible the layer adhesion and get isotropic properties in all directions. Which options are commonly available? I don't know. You can play with lasers, with infrared light, with LED. Everything has its advantages and disadvantages. And again, if you want to explore them or you want to talk about them, let's do it later because we don't have a lot of time. But one very good example is in the 12th pavilion is the LFAM system that is already developed. And they are using LED light just to improve the power density of their lights in specific spots. That allows to warm up the layer and consequently get like the perfect layer adhesion. Yesterday I was talking with them, and they are getting with PKK almost the same mechanical properties in X direction and in Z direction, around 100 megapascals. So that is incredible. Another example, the chamber heating up. When you are at home, when you are in a small scale, that is quite easy to raise the temperature up to 60 Celsius. Maybe if you have a very good printer, you can reach like 100, 120 Celsius. But that is not happening in larger scale. In larger scale, you have a huge room that must be heated. And that is not easy. So for example, what we are using is infrared light that allow us to increase the temperature of the size that we want, and in this way decrease the thermal gradient lost. Well, next step, design optimization. After defining what we want, how much to be the tank, we have to check if every part of the tank can be printed, and if the mechanical and the structural properties of each part is good enough to print the final tank. Why? Because we only have 1-2 shots. So usually, what can be done is to take the whole design, break it in different parts, and test each part separately. Then you test the part and get and improve step by step. Finally, get an optimized model that sometimes can be like looped once and again till you have like the definitive model. This is an example. When you are printing in low scale and small scale, if you don't have like good properties in the bottom of the print, maybe you can add 1, 2 layers, 3 layers, but that can't be done when you are doing a technical print. In this case, we were trying to reach 2.5 millimeters thick bottom. But only a small fail into the layer, as you can see, this is by placing like this is a picture by placing like the model into the light. You can see how the light is going through the model. This is because there wasn't enough material there, and consequently, the liquid nitrogen that will be inside will leak it. So you have to check every very step to improve it and ensure that everything is where it must to be done. Everything is done by design optimization and path planning. Well, another step is the distortions. Sometimes when we're having like thermal contraction or we are developing our models, because the printing process itself, it generates some defects that can affect the final model. So you have to define what is going to happen once the model is cooled down, and in this way, redesign again the model to avoid all these fails. Sometimes, for example, as in this case, in order to decrease material or achieve like the best properties, what you can do is to just modify like the angle or how you are printing. Well, let's go a bit faster. During the slicing, another small part that can happen is that small fails. As example, here we have in a cross-section of our model that we were having a small spot with a small cavity. Well, you have to improve it perfectly to achieve like perfect layer deposition and avoid any hole, anything. Almost finally, we have the printing organization. When you want to print 100 hours or 150 hours, everything is an issue. So you have to be very sure that who is going to check what is happening to the print? How is the print? What is going to happen if any issue arises? So you have to monitorize like the printing process and be sure that if anything happens, the guy who is there checking the print will be able to modify or to change the things to avoid any failure. And finally, printing defects. I bring here, I don't know, 3 small sections of our model. What is the weight of these models? 5 grams? This is not an issue. I print it again, and I print it again, and I print it again, and it was fast. I mean, again, 2 hours, it was done. This is not happening in large scale. This is a 40 kilogram print. And when this fails, you are losing not only 40 kilograms of print. If your material is expensive, you are losing also a lot of money, a lot of effort. So you have to be very careful with all the steps. Finally, you have to develop a preventive strategy if anything happens and if you can't avoid it, how to solve it. As example, this was when the material was broke. If the print stops and you need to start it again, you have to ensure that the print or the layer arises again, like the temperature, and you are able to start printing it above it. So you have to have a strategy. You need a path planning strategy to start heating it up again and raise the temperature to improve the layer adhesion and get the model you want. Finally, I would like to thank the 2 guys that make all this work possible, Xavier Perez and Manuel Montero. And nothing. Thank you, and please ask anything you want, because I will be more than happy to talk with you.
Thank you very much. We have time for one quick question from the audience, if anybody would like to ask one, or you can catch Andrew afterwards. Where will you be? Where will we be able to find you?
I'm downstairs. I'm Man. We are in Man, so we are in the hall 11.1. This actually, it's not. Maybe it's at the beginning. Give me a sec. If you are interested on it, I got it in the first slide. So. There we go.
There we go.
Level 1
Level
is
1
69.
is 69. So that's not far. Okay.
No. Come,
Perfect.
please.
Thank you very much.
Thank you.